Hi all, it's Lasky from Malfine's Lab channel, and today, as a part of preparation to the Flare 8 challenge in September, I will show you the solution to the second challenge from last year, which is called Garbage. If you don't know what this entire Flare challenge is about, please refer to my first video, which will be linked in the top right corner. And basically right now, just let's move into the solution. So we will extract this second challenge, and we can see the message. One of our team members developed a Flare challenge but accidentally deleted it. We recovered it using extreme digital forensic techniques, but it seems to be corrupted. We would fix it, but we are too busy solving today's most important information security threats affecting our global economy. You should be able to get it working again, reverse engineer it, and acquire the flag. So basically, we have a binary that we need to run and possibly reverse engineer to get a flag. And let's just try to run it first. And unfortunately, this won't run. So that's a little bit of a pity, because of course there can be plenty wrong with this binary that makes it not able to run. So let's take a look at it. There are a few tools that can be used to check the binary structure and entire binary structure. One of them is CFF Explorer, which is a very good tool for this challenge, and actually the official solution I think is in CFF Explorer. I will use PBER, which is a solution developed by Hasherazadeh, which is a great Polish reverse engineer. You should check her out if you don't know her yet. And she also develops a lot of nice tools like this one. I actually like the PBER more than the CFF Explorer, so I will use this one, but you can use any of these tools, to be honest, to solve this challenge. The solution to this challenge I will show you is quite complex. It's how I solved this challenge personally without looking at the solution. So after a brief look at the binary, we can see a few things. So first of all, what PBER does is basically parses Windows binary format and show you all important information about the binary together with the hexadecimal and ASCII representation and things like this. So if you don't know anything at all about the P format at Windows and how it's constructed, I will link few materials in the description below, because this video won't be explaining everything about it, because it would take a long time for us to go through everything that goes on in the PE format. So I will assume you already know some of this. But I would just make a very short introduction. So basically, P has a few headers: the legacy DOS header, then the NT header, which gives us a few information about the file, like, for example, the timestamp of the compilation, pointer to the symbol table, etc. It's not always used. Basically, the architecture, and what is important here is the section count, which tells us amount of sections in the file. In this particular case, it's 3. And we have an optional header, which is not really that optional, but it gives us a lot of important information about the binary, like size of the code and entry point to the code, which is really important. and the size of the image, and gives us few other important information like import directory, resource directory, and you can already see that these parts are highlighted in red, which means something wrong with them, probably. We will deep dive into what's wrong in future. And here you can see the section header. So basically the sections in the files. If you ever look into this kind of tools showing you the portable executable P format, you will know that traditionally in Windows there are sections like text, iData, relog, rscrc, which we have also here, etc. Here we only have 3 sections, and 2 of them are called UPX0 and UPX1. And anyone who ever did some kind of unpacking of the code will probably know this is a very popular open source packer called UPX that's basically used to pack binaries, not only malware but any binaries really. It's quite easy to use, but it's also quite easy to unpack. Actually, it's one of the few packers that also provide an unpacking capability, so we could actually try to just unpack this binary with IPX-D and the binary name. And if it would be a normal packed binary with UPX that was not corrupted, then we could do it possibly, but here it's not that easy to do because it says the file is possibly corrupt and it basically fails to unpack this binary, so it won't be that easy. So we need to take a look at this binary. Also, if we want to execute this binary with x32 debugger, it will say, so that much happens. You can see here on the bottom it says invalid P file, so it basically fails to download the binary. So what we can see about this binary is basically the binary is truncated. And how we know it? If we look at the section headers, we already see this is highlighted slightly in red, and the row size of the resource section is 124 in hexadecimal, which is kind of strange because if we look at the optional header, the phi alignment is 200, and for those who don't know, the phi alignment it's basically means how big it's an alignment of every section when the file is in the disk. So we have a section alignment, and this is the alignment of each section where when file is mapped into the memory, and we have a phi alignment, which is the alignment of each section when the file is on the disk. So it basically means, in short, that every section size on the disk should be multiplication of 200, and here we have 124, but if we double click on it, it says 400. So this section wants to be a 400, but the file is basically means the file is not big enough, and it's truncated at the end. So if we look here, we can see there's some manifest, and this manifest is basically truncated at some point. So this is probably related to these forensic methods they mentioned in the challenge. So we'll also use hex editor, namely xhd, for this challenge. It's just a little bit easier for me to edit the hex values in there. Actually, PBeer also allows for it, but I will use this as well. And let me just go to this challenge. And if we go to the bottom, we can see our resource section starts at 9E00 offset. So it starts here, and it should be 200 in length, but it's only 124. So we could add additional zeros here. And yes, I want to change the size of the file. And we need to add them a few times more, because now our length is only 140, so we want to add a little bit more, still a little bit more. I think it's easy to just calculate the size, which is basically hex of 0x9e00 plus 0x200, which should be 0xa00. So until this offset, we need to add zeros, and it's already enough. So we will stop here. We will save it. And now our binary is aligned to the size of the of how big each of its section is supposed to be. If we reload this, we can now see the section header change to 200. But it's still highlighted in red because it actually wants to be 400. So let's make it 400 instead. So actually what we want is additional 200 zeros. So let's just copy paste this. I think we need a few more. Okay, one row too much, or actually 2 rows too much. I think that's enough. If we check, it's 400 in length, should be fine. Let's reload it again. And now our section header is no longer highlighted in red. Let's try to execute this. And we can see it still doesn't execute, but it's the error message has changed. And it says it's fast failed to start because it's side-by-side configuration is incorrect, blah, blah, blah. This is quite a strange error, which when I ran into for the first time, long time ago, analyzing some malware, not actually related to this challenge, I spent a lot of time debugging, but it basically means your manifest file is damaged and it cannot read it. So the easiest solution is just to get rid of the manifest file. So the easiest solution is to just remove the entire resource section. Maybe not remove, but just clear it. So if we clear it, we will save this executable to garbage.exe. Maybe call it, let's just save it to the same binary. We need to reload after that, and we can try to run it now. And as you can see, it actually kind of runs, but it crashes. So it's a progress. Let's see how we can actually make it run and what's the issue here. So we can run this application, but it crashes, but this means at least we can execute it in our debugger and see what's wrong. So basically, this is our entry point, which we can also see in the bar. So this is our entry point and this is code. And basically code is some kind of assembly instruction that's not doing that much, some kind of loops, etc. But the first issue we can see is will be probably here. So there are some calls, but the problem is our binary doesn't have any imports. So basically, unless this code is completely like position independent kind of shellcode that resolves the DLL location in memory and the kernel 32 DLL location in memory, and then resolve all the addresses of the function based on that, because it's doable. But this is not this kind of code, so it basically needs some imports, and I'm assuming the imports were removed together with the truncated content. So if we go to the optional header, we can actually see our import directory is placed in this virtual address, and as we can see, it's contained of all zeros, and same with our relocation tables. So yeah, we need some kind of import table, because if we look here, we can see that what's causing issues is this core. So if we go to here, the binary is running quite well. But if we step over it, we directly have an exception, because this pointer to ESI plus this number is basically equal to 0. And this is because there should be a import address table under this under here, but there's not. So if we check this address, let's ignore the 4, because this is the image base for 400,000 in hex, but 19218, if we look at here, this is actually within our import directory. So this is a pointer to the import table, but the import table is removed. And let's stop it for now. What I did during solving when solving this challenge, it's not the best method maybe, but I just had some kind of a working 32-bit binary here, just a simple injector that I wrote for completely different project, but I use it just to pack it with the UPX. And when I pack it with UPX, I can see we can even open it in bar, for example, to see. So if we go to the entry point, we can see here the code is quite similar, and we actually have a very three similar cores in here. So if we open it in x32 debugger, when we copy this binary here, we just can run it right now, and yeah, then it will run. And if we go to our entry point, we can actually see there are very similar cores in here, and we can see these cores done by UPX. The first one is actually to kernel 42 load library A. The second one is to the get proc address, and the third one actually is only called when something goes wrong, but it's to exit process. And There are also two indirect calls in here. If we go there, we remove breakpoints from here. You can see this is the core to the virtual protect. So we will basically need this for functions imported. So the easiest way to do it, maybe not the easiest way to do it, but the way I did it is, let's stop this one and let's open this file in our hex editor, and this is the import table. And basically we could possibly create another section and just create an import table in there, but I tried this approach, didn't work because there are some hard-coded values that lead to the old import table, so that are created by linker during the compilation. So it basically means by hand changing every single offset in the code. So this is not that good. So we will just basically need to recover the import address table in here, which this is the virtual address after mapping to the memory. This is the address after when the file is on the disk. So this can be quite confusing sometimes. So we just basically need to go to this offset. And we need an import address table in this offset. So the way this code works here, let's restart our other packet sample. And so we're interested in this here. So this is basically the pointer to the import address table entry. So this string kernel32.dll, it's being pointed to by this address, which is EAX plus ESI plus this 228.1 DC hex value. And this hex value, if we look in here, let's open the injector.exe. We can actually see that this is, here, 29.1 DC. It's a relative virtual address of the import directory. So it's actually this minus 1000. It's 28.1.dc. And why minus 1000 in hex? It's because the ESI, if you look at here, ESI is a pointer to the base of code. So the entire binary injector.exe is mapped to this address FA0000, and this is like a base address of the binary, which is relative to all the virtual addresses. So the relative virtual address is actually address of the function in the code minus this base address. But what the ESI holds is actually the pointer to the beginning of this UPX0 section, which is this plus 1000 in hex, and that's why this relative virtual address 28,001 DC is 1000 less than this import directory table, because this is related to the base address of the binary, which In this regards, it should be for 40,000, but the binary was loaded into a different region in memory, sorry, for 100,000. So if we go here and follow this calculated address in the dump, we will see this points to this kernel 32 DLL. And this is, as we can see, actually part of the import address table. So what is important in here is that this pointer to this string is calculated in here from EAX plus ESI plus this number. And the ESI is always pointing to the base of UPX0 section, but the EAX is calculated somewhere higher. And it basically depends of the length of what is prepended before the name section in the import address table. So this is like a pointer table here before. I will show. We will look into this a little bit more in a second. So length of this is probably should be 90 in there. What's important, we can get it from the EIX value, so we don't have to calculate it. We just can get it from the EIX value, and then we will know the length of our import table and when we should start our to put our strings. This is important because this will be later referenced in the code. So what I'm trying to say is going to our CTF sampler. We can set a breakpoint in the same exact place, and we can see our ESI. It also points to the base of the code, which in this case is 401,000, which we can see in the memory map. It's a base of the UPX0 section, which is same as in the other sampler. And our length of the import address table pointer part is 58. So this is important, and this is something we should take a note of, which is EAT length 0x58. This is important for us. I will show you why. So let's stop it for now, and let's go back to our hex debugger, or sorry, hex viewer. And if we go to our garbage.exe sampler and click on import directory, we will be redirected here to the beginning of the import directory on the disk. So we need this offset. It's 0x and this, and add the calculated value of the value we saw in the EIX register, which is the length of the initial size of the import address table. And this is a place when we need to put our kernel 32 DLL string, because this is how it will be referenced. I don't know if it makes any sense for you, but I hope it will make soon after I show you this. So we need to go to here, and in this exact location, we need to paste this string, kernel 32.dll. So we'll just copy paste this here. And when I save it and restart this sample, we have a breakpoint in the same point here, and you can see now it's not pointing to nothing, it's pointing to the kernel 32 DLL string, which is great for us because now this will be passed as a parameter to this call. But this is not yet calling anything because this call is also pointing to the part of import address table. But unfortunately, sorry, misclick. Unfortunately, this is like, as you can see, this is slightly before our kernel 32 DLL string. So this is actually pointing to the pointer to the it's a pointer to the pointer to the function that should be called, but there's nothing in here yet. So what we know is we need here a pointer to load library A function. How we know that? We know it from the other sample. So if we open the other sample fast, we can see this is the sample I created and packed with the UPX. And if we go to our breakpoint here, we can see this is calling kernel 32 load library A. And if we actually follow this address in dump, we will see we are here before the string kernel 32 DLL, but this has some address in here. So this address is actually pointing to, if we follow the pointer and not the address itself, it will point, of course, to some code, but generally speaking, yeah, this is pointing to the start of load library A. Yeah, which is good, which is what we want. So we need to replicate this in our garbage binary. I mess up with you a little bit. These pointers are, of course, already resolved in the memory. So what we need is the import address table from the disk, which, as you can see, it's easier to see in the P bar. We'll go to our injector.exe to the import table, and if we click on kernel 32 DLL, this has call to the load library A here, and here actually it points to this tank 29232C6, which is a point to the string load library A. And while why was it different in the memory than it's in here? Because if we look at here, this is actually pointing to the different address. So this is the same part of the code, but here it's pointing to 0292C6. Why I'm reading it backwards is because it's in Little Indian. So this is pointing basically to this func 292C6, which is like we already said, the load library A string. But in memory, this part was pointing directly already to the code of the load library A, actually to the jump, to the place in the code that will cause a jump to the load library A code. And this is done via the executable loader, the PE loader, which will resolve the import address table and replace these relative jumps, relative addresses with real pointers to the code of the loaded library. That's why this was different between memory and the file. So now what we need to do is basically replicate this, what we have in our injector.exe, in our garbage.exe binary. So it can be actually as easy as copying all of this. Yeah, like I said, pbear is sometimes tricky with. I have honestly no idea how to make this selection work the way I want. That's why I will use the HEXD hex editor, and I will go here and I will take this first four, actually the first four the first four functions imported from kernel32.dll. These are these four, and I will basically copy paste them here, but we need to save some space because as you will soon notice, there will be one more binary needed to load, so we need a place here to put it. Actually, it would be nice to just have a similar offset. It doesn't really matter. I will just paste it here. So we have it here, and when I save it and reload it here, we can see that we still don't have any imports, of course, because our import table is not finished. But if we go here, we can see this these strings I copied here. So what we need to do right now is add an import. It will create this kind of filled-in structure of the import address table, which is basically the original first chunk, then zeros, then these 4 bytes are the relative virtual address to the name string, and then there's a first trunk. Yeah, how it works is basically like this. So this is already in the injector.exe. This is already working import address table. So it has this in this offset. It has this kernel32.dll import. When it points to this kernel32.dll name, and the first func is actually pointing to pointers to the functions itself. So this is pointing to the first of this, and then they are resolved one by one, like 4 bytes, then another 4 bytes, then another 4 bytes, then another 4 bytes. As long as there are only zeros, then it stops. So I hope it will become clear very soon when I make this. So the original first chunk will always be 0, so I will just remove it. And here we want a pointer to kernel32.dll, which is 083. We will use this one again, 8030 plus 4 bytes minus this. It should be 19234. So this should be pointing the name array should be pointing to the kernel32.dll string, not the load library string. We can actually add it in here. We don't even have to use the little Indian, but just to show you how to do it. This is already correct, 0192. We only need to change the last part, which is 34, and then our name will actually fill in here, which is nice. And then our first chunk we need to change into 00. And this is actually pointing to the place that will be point to our load library A string. which is the place we don't have yet, but it's okay. We will just use some stuff after someplace after the our loaded functions. So let's make a little bit more space in here because we will need to import one more function. And let's just say we will use A100, which is still within our section, I believe, or just use it. We can even do it here, like A14C, it's perfectly fine, which is in the virtual A14C, which is in virtual 1934C. So let's fill this in. 01 93 4C, and here we actually need this pointer, which is pointing to the load library A string, actually 2 bytes before. So this will again be 01, and you can already see this filling in when I'm writing 01926A and C, D, E, and now we have a load library A as our first import, which is cool. So just to show you, because I know it can be a little bit more confusing what we've done so far, I will save this executable, reload it. It's actually not necessary, but okay, just to have everything filled in. And then if I open it again in the debugger, you can see here it's loading the kernel 32 DLL, and here there's actually a problem. So this is still pointing to the wrong place. Okay, now I know what's the issue here. I think I know what's the issue here. So the issue here is we put this somewhere below, but I mean not here, but this section here should be actually 2 rows lower. I think I put it randomly there because I thought it would be okay, but it's not okay. We all learn from our mistakes. I will just do it like this. Let's go to the imports. Let's go there. So this is our name, RVA. This is pointing to 19218, which we can also calculate the physical address from, just for our convenience. This is calculation of the virtual address from the physical address. So let's just reverse it. So basically we will subtract our virtual base from our virtual address, which is 19218, and then add our physical base, which is 0x900, and this is our physical address of where is this pointing to. So I will just go there via our hex editor and this should be here. So basically this section with the imported functions I've put randomly somewhere here. This should be actually in the place that is being pointed to by the code. So actually in this 19 to 192.1.8 address. So this we will change to 19. What was it? 192.1.8. Yeah. We even noted this and then didn't make use of it for some reason. That was a mistake. So I will just take this and copy it from here and just clear it and just copy it to here. So now we have this load library at the correct address, in my opinion. Let's just save this executable and see if it's correct. We first need to stop the debugging and save it again. Now let's reload our debugging. And now we can see, yeah, it is pointing to the kernel 32 load library A, which is perfect. Great. So we already imported one library and one function. So now we need just to recreate it for the others four, which is as easy as basically adding other pointers to these strings just after this one. So this is 19,218 and this is pointing to here. So next one we want is the exit process. So like I said, the order is important. So next one we want is the exit process, and we only need to calculate our length of this to know the current address. So we will get this func address, which is the pointer to the load library A string, which is 19 to 26 A plus len of load library A plus 2 empty bits. If I remember correctly, this should be a correct address. So we just need to put it in there. So this is 01927C, and perfectly it's a pointer to the virtual protect. And so yeah, the one after the load library is the virtual protect. We should actually point it to there, and the virtual protect should be the last one. So we can already make use of it, and we will know it should be there. And we will modify this to point. Let's calculate the pointer to get pros address first. So we will just kind of fill in this table from the end, not from the beginning. It will be a little bit easier. Get procs address. But we actually want to subtract this because this is pointer to our load library A. and we also want to subtract these two, and this is 192.5a, so it's 0.192.1a, 0.192.5a. Why I said why is 1a in here? Yeah, better. And now we only need to modify this one, so let's subtract length of exit process and another 2 bytes. Something wrong. Oh wait, we forget this. So it's 0.19251, 0.19251, or maybe 50. Okay, so our import table for the kernel 32 DLL library is finished. So let's see if how our binary will behave. So I will save this executable as garbage.exe, and then I will run it again. So we can see it's loading the kernel 32 DLL library, which is great. Then it's running the get proc address for the get current process function, and then other functions like write file, terminate process, create file. So it's basically resolving all these memory, all these pointers to these addresses. This is how a lot of loaders also, my malware loaders and packers work. So they basically just import these four functions, which is load library 8, get proc address, virtual protect, and virtual alloc or virtual protect, and yeah, basically what you need is load library A and get proc A, and then you can resolve every other API call from any library, because you can load the library with the load library A and then resolve the API call function with get proc A, like in this case. But if we remove this breakpoint, we will see that we go back here. So it tries to resolve some other string, this time in the 0x65 offset. So not 558, but we should have another string and 0x65 offset, another string with another binary library probably. And then it's tried to load this library via load library 8, but of course there is nothing being passed to this. So the library won't be loaded and the program will exit. Not even crash, but just basically exit, so it still won't work. And how do we know what library it wants to load? So we have a slight hint in here. So it's actually trying to access some string already via this register ADI +4. And if we actually follow this in dump, we will see this pointer to the string shell execute A. And if we check in the documentation, the shell execute A function is part of the shell API, which is basically the shell 32 and DLL. So we can see it's a shell 32 DLL shell execute a function. So in that case, we know it tries to load something from the shell 32.dll. So most likely it is a shell 32.dll that it tries to load. So we know this offset 0x65. So if we take our import table base, which is basically this 0x191 tc plus 0x65. This is address when this string wants to be. Let's calculate it. It's basically directly after kernel 32.dll, but let's calculate it like we used to. So we have this calculation from the virtual address to the physical address, and then let's go there, and we can see it's directly after kernel 32.dll, and we can put it here, but we need to stop debugging first, and let's try to see after adding this string if we can load this, if this binary will even work. So normally we should probably, if we want this shell 32 to be properly imported, we should do as well as with the kernel 32.dll. So put it in the import address table, added this name and array, added at least one imported function like here. But actually, because this string is only passed into the load library A, and the load library A loader will take care of everything, and then we'll call also the getproc address to resolve all the function. I think this should be enough if we just basically run it like this. Let's see. The way I solve it, I actually imported the shell 32 with one random import, but I don't think it's necessary. So first it loads kernel 32 with all the function, and now as you can see it tries to load the shell 32.dll. And okay, I wanted to show you more, but I didn't set a further breakpoint. Anyway, our binary is fixed, and this is our flag. We solve it. So I know this this movie was quite long. I didn't plan it to be that long, but I wanted to explain you a little bit about how the import address table works, because this is also important, and this is like a main learning thing from this challenge. So I hope after my explanation was not maybe too chaotic. I know it was a little bit chaotic. I hope it was not too chaotic. You could learn a little bit about how to manually recreate the import address table in the file. So this was my solution to this challenge. There are more solutions to this challenge. I will link in the description of the video below the solutions by the challenge author, because this video is already too long to go through other solutions. But I think this solution is quite hard one and quite complicated, but also very good for learning about how the import address table works and how the executable files work in Windows. So I hope you like this video, even though it was quite long and maybe chaotic, and I hope to see you in the future videos. Thank you and have a good day.